Parental guidance is advised for the following program.
One 1998, 1999, 2000. Oh, Mr. Yap, what are you taking?
Me, I'm taking a steroid pill.
Steroid?
Yeah,
like the banned substance steroid?
Yeah, to
Hey,
increase my muscle mass. Can't you see that it's making a difference?
Wait, kids. We cannot take drugs, okay? Say no to drugs. Don't try this at home, okay? Now, jokes aside, I think we'll focus a bit more about what is the drug that you are taking, right? This is going to be a steroid, and we have the molecule over here known as aldosterone. Right? Now, if you look at this molecule, we're going to observe the functional groups. So let me just show you some of them that you've already learned before. The first of which is going to be a CC double bond. What kind of functional group is that?
This is an alkene functional group.
We have seen this before, right? Now, we have also saw an OH over here. There are two OHs. What functional groups are those?
Right, so the one on the top is on the right is a primary alcohol. The other one is a secondary alcohol.
Right, and we also observe that there are two more new unknown functional groups over here. Mr. Yap, can you bring us through it? What functional groups are this?
Right, so this is a C double bond O, or what people call a carbonyl functional group. Now, if you want to look at what is a carbonyl functional group, you need to focus on the carbon that is directly bonded to the oxygen. Now, you look to the left and the right of that carbon, see what it's bonded to. Right, so if it's bonded to at least one hydrogen, it's going to be called an aldehyde.
So this is going to be an aldehyde.
Right, and if the carbon is bonded to two other carbon atoms, and that's called a ketone.
So this is going to be called a ketone.
Yep. All right, so to quickly summarize, carbonyl compounds can be subdivided into two kinds. One is called aldehyde. Look at the carbon, it must be bonded to at least one hydrogen. But for a ketone, it will be bonded to two other carbon atoms.
That's right.
Oi, no more already, Mr. Leong. I want more.
It's okay. I'll teach you two methods to prepare more of your steroids.
Okay, show me.
Let's take a look at the first one. That's on reaction 7.4. We say that our carbonyls can be prepared using an alcohol through oxidation process. Now, we learned this in hydroxyl compounds that is very important for you to know what is the classification of the alcohols before it undergoes the oxidation, right? If we start off with a primary alcohol, which is over here, that's where your C is only bonded to one R group. We can oxidize this to an aldehyde. But you have to bear in mind that the conditions that you need must be fairly controlled. We have to use a weak oxidizing agent, dichromate, and as well as we must heat with immediate distillation. So you can help me to add this into your notes as well. Mr. Yap, what happens if I don't do immediate distillation? Let's say I decide to reflux it.
Right, so the primary alcohol will be oxidized to the aldehyde, which will be further oxidized into carboxylic acid. So you cannot stop the oxidation process halfway and say, hey, I want the aldehyde. Right? It doesn't work that way. If you don't do distillation, you will not be able to isolate the aldehyde compound.
That's right. The other way is to look at secondary alcohol, but the product you're going to get is going to be a bit different, right? You're going to end up with a ketone. So we're going to use any kinds of oxidizing agent, potassium manganate, potassium dichromate, that is fine. But be careful here, just to help me to change this, we don't heat with distillation. We usually do this under reflux. Okay, so bear in mind, primary alcohol can only get you aldehyde, secondary alcohol can only get you a ketone. So that's the first way of getting the steroids and carbonyl compound for Mr. Yap to grow bigger.
Right, so the other way that we can synthesize ketone is to do an oxidative cleavage of an alkene. So if you look at the carbon-carbon double bond, focus on the left carbon, that carbon is bonded to two different R groups. So what does oxidative cleavage or strong oxidation of an alkene does is that it will break the carbon-carbon bond down, right? So that carbon on the left is bonded to R groups, it will be converted into a ketone. Right, on the right, that carbon, because it has a different structure, is going to be converted to a carboxylic acid, right?
So now we're going to take a look at the structure as well as the chemical properties of a carbonyl compound, right? So we recall again that a carbonyl compound must have a C double bond O. There are two R groups attached to it. If one of them becomes a H, it becomes an aldehyde. If both are carbon, it becomes a ketone, right? Now, the important thing is we're going to focus on this carbon. Now, notice that this carbon, right, how many bond pairs and lone pairs do you see, Mr. Yap?
Right, so there are 3 bond pairs and 0 lone pairs.
And what kind of shape do you experience?
This will be trigonoplanar.
Yep, and hybridization?
The hybridization of the carbon will be sp2.
That's right, so it's trigonoplanar, sp2 hybridized, right? So in this case, the idea is that it is going to be flat on a piece of paper. So can I say that carbonyl compounds are trigonal planar then, Mr. Yap?
Right, so that's a common misconception that students would have. Now, about the carbonyl functional group, it is indeed trigonal planar. However, if you look at the R groups, there are other carbon atoms there. It may or may not be trigonal planar depending on the situation. So you guys have to be careful with your phrasing. All right, so you always say that the arrangement about the carbonyl functional group is trigonal planar, right? Not the carbonyl atom or carbonyl molecule is trigonal planar. That's not correct.
So we'll take a look at the chemical properties of a carbonyl compound now. So here comes the million-dollar question. Is a carbonyl compound an electrophile or a nucleophile? So if I take a look at the structure, the O is a very electronegative atom, right? As a result, this carbon will be very electron deficient. So is this a nucleophile or electrophile, Mr.
Right,
Yap?
so if it's electron deficient, delta plus is going to be an electrophile.
That's right. So if it's electrophile, it is going to get attacked by nucleophiles. So in general, if they themselves are a electrophile, they will not undergo electrophilic reactions. They will undergo nucleophilic reactions, right?
Okay. Now, in terms of the carbonyl functional group, if you look at the functional group, there's an unsaturated bond, right? A double bond, right? So in terms of the type of reaction, do you think it will undergo an addition or a substitution reaction, Mr. Leong?
Well, if there's a multiple bond, there is a pi bond which is typically weaker than a sigma bond, right? So I feel that it is going to break, and as a result, you are going to introduce two different substituents that can be added across them. So I believe it's going to undergo a addition reaction.
Yes. So in other words, to put it nicely, carbonyl compounds generally undergo nucleophilic addition reactions.
So to summarize with this simplified mechanism, this carbon is electron deficient. It is going to get attacked by a nucleophile, and because this carbon itself can only hold 4 bonds, right? It has no choice but to give up its last bond. And this last bond is going to give up is going to be the
Pi bond,
the weak one, right? And this bond is going to break, causing to have it only have just one sigma bond left. Now, the next part is we're going to take a look at carbonyl compounds and we'll compare it against different functional groups. The first of which is going to be an alkene. Now, if I take a look at the two structures, you will notice that both of them have some similarities. Mr. Yap, can you run us through that?
So the similarities would be both of them have actually pi bonds, right? So, but if you focus on the alkene functional group first, right? So it's pi bond between 2 carbon atoms. There's no difference in electronegativity. So the bond is said to be non-polar, and it's because it's a carbon-carbon double bond, it's electron-rich. Right, so it's going to act as a nucleophile, and therefore it's going to attract electrophiles. Okay, but if you look at the carbonyl group on the other hand, the carbon now is bonded to a more electronegative element, oxygen. So there's going to be a separation of charge, causing a delta plus to be on the carbon and a delta minus on the oxygen, making the carbon susceptible to nucleophilic attack.
So in general, we can say that alkenes, they undergo electrophilic reactions, right? But your carbonyl compounds undergo nucleophilic reactions. That is the difference between them. But what is the similarity between them, Mr. Yap?
They're both unsaturated compounds, so they will undergo addition reactions.
So you can break your pi bond, and as a result, you're going to add 2 things across the 2 atoms, right? All right. Now, the second functional group we're going to look at is going to be comparing between an aldehyde and a ketone now. Right? So when we look at reactivity, right, we are always interested in the carbonyl carbon, which is electron deficient, and we want to see how easy the nucleophile can come in to attack them. And how easy really depends on 2 factors. The first of which is called an electronic factor, and this is really looking out for the number of R groups that is directly attached to the carbon. Now, if I take a look at a ketone, you have 2 alkyl groups, right, Mr. Yap? Can you tell me what kind of effect is alkyl groups going to exert?
Right, so alkyl groups are electron donating in nature. They will donate their electron density over to the carbonyl carbon, making that delta plus there so-called less delta plus, right? So it will make it less electron deficient and therefore less attractive to a nucleophile. And we say that it's less susceptible to nucleophilic attack.
So this means that actually ketone is less reactive than aldehyde, right? That's what I can say. So that is the first factor that we're looking at. Now the second factor is known as the steric factor, right? So imagine that now we both will form a ketone.
So we are the R groups of the ketone.
Right, there's a C double bond O right in the middle of us. Okay. Nucleophile, come
and attack us. Right, so as you can see, the nucleophile cannot squeeze in between us because the 2 of us are very bulky. We are very big size and muscular. So the nucleophile don't have space to squeeze between us. However, what if we are an aldehyde? So I'll push him away. The R group is gone. So now there's just a single hydrogen atom here. So hydrogen atom is a very small atom. It's negligible in size. So now the nucleophile can actually squeeze in between us and attack the carbon. So this is what we call steric hindrance. The bulky groups are going to exert steric hindrance, hindering the approach of the nucleophile. Okay? Okay, thank you. All right, Mr. Leong, please come back, please come back.
Okay. I'm coming back to summarize things for you.
Thank you.
Okay, so far what we have seen is the comparison between aldehydes and ketones, right? So in general, because of these two factors, we can say that ketones are generally less reactive as compared to your aldehydes, right? So this mechanism, we're going to see this in class, all right? So see you in class. Bye. Oi, stop eating.
Okay, sorry.
2004. Oh, done. Wait, what was wing? You said wing?
I'll W-I-N-G it. I'll wing
Oh,
it.
wing it.
as we go along. Yes. Boomer.
You took my stuff and so I don't know what's going on.
Then you take it
Say
back
anything.
up.
Action? And
Oh, actually, sorry.
Action.
chemical property, okay? Mechanism in
Where's
class,
all this? Where's all this? It's not here.